Welcome back to the NPTEL course on tectonics and geodynamics. This is lecture 11 and we are going to we've discussed in the last classes about triple junctions and their stabilities. What we will do now is to look at specific triple junctions. We will look at the evolution of selected triple junctions on Earth. So let's just get right down to how a few selected triple junctions on Earth actually evolve with time, because these are extremely important and interesting for us to actually see how the movement of these triple junctions actually controls the geometry of how the plates are moving on Earth. So let's just go and start off with a recap of what we did. You remember that triple junctions are basically the junctions between three plates on tectonic plates on the surface of the Earth. There can be 16 types, right, of triple junctions, 16 types. What we do is to refer to them in terms of the types of plate boundaries. So F refers to a transform fault. So these are transform faults. You have R's, which are ridges or divergent boundaries, and you have T, which is trenches or convergent boundaries, right? So these are 16 types. Of these, right, we just know that a boundary which is of the type RRR, that is a ridge triple junction, these are always stable. If you have an F triple junction, three types of transform faults meeting at a point, this is always unstable. The remaining types of triple junctions, most of them are stable under certain conditions, but they can also be unstable. Those which are unstable would try to evolve into some kind of stable geometry with time. So in essence, now what we will do is to look at three different types of triple junctions on the Earth. We'll look at two specific ones, an RR type and a TTT type of triple junction. Then we'll go on to something that is actually really fascinating, and it shows you how different geometries can evolve on the surface of the Earth simply because of the movement of the continuous movement of plates on the surface of the Earth itself. So let's go into the next part, right? Just to give you a brief overview of the plates of the Earth. Remember the sizes of the plates. Now this is the plate on which we are, the Indian plate here. That's the Indian plate. The largest plate that we can see is the Pacific plate, right, which comprises most of the Pacific Ocean, right? Then you have the North American plate. The North American plate goes this way and actually passes a little bit southwards, right? And it actually passes just to the north of Japan. Probably includes a little bit of the northern part of Japan. So it's a fairly long plate which has a peculiar type of orientation. The North American plate also includes a continent as well as an ocean, so it extends up to the middle part of the Atlantic Ocean. You have the South American plate, which includes most of the continent of South America, right, and much of the South Atlantic. You have the African plate, mostly surrounded by ridges, but it's got a few trenches right in the northern part in the Mediterranean Sea mostly, right? And we have the Indian plate itself, which has got a convergent boundary in this particular segment, right, and up to about here. But there are ridges on this part, right? Not many transform boundaries that we know of, but we think that the Indian plate, anyway, it's evolving, and what used to be called the Indo-Australian plate is now believed to be actually separated from the Indian plate and the Australian plate by a zone of diffuse evolution, okay, which is sometimes referred to as the Capricorn plate here. Now, of these different plates, now the parts that are of importance to us would be the ones that are in the Pacific and in various parts of the Pacific, because this is where most of the evolution of the plates was discussed. Now, apart from the larger plates like the Eurasian plate, etc., there are smaller plates, right, that we'll be discussing in this class. So, for example, you have a small plate called the Caribbean plate and the Scotian plate here, right? But more important to us in the course for today's class are these plates called the Cocos plate, which is here, and the Nazca plate, which is here. The Nazca plate is actually supposed to be the fastest moving plate on Earth, okay? And we have the Cocos plate here, which is a small plate, right? So just to the western part of Central America. You have a very small plate called the Juan de Fuca plate to the north, and we'll be talking very briefly about that towards the end of today's class. So let's just now go into seeing, right, what we see around this earth. Now, where are the triple junctions located? Now, not all triple junctions are shown here. These are the triple junctions that are important with respect to the orientations of ridges and transforms. So you have a number of them shown here with respect to India. So this is India here. So we have a triple junction here effectively between three ridges, right? So this is the Central Indian Ridge, Central Indian Ocean Ridge. This is the Southeast Indian Ocean Ridge. This is the Southwest Indian Ocean Ridge. And this is called the Indian Ocean Triple Junction. This one is called the Indian Ocean Triple Junction. I think it used to be called the Rodriguez Triple Junction before. It's now more appropriately called the Indian Ocean Triple Junction here. So you have another triple junction here. It's actually shifted a little bit from its position. So the position should be somewhat here. So you have a ridge called the Carlsberg Ridge meeting with this Levantine transform system, and another ridge system which is represented by the East African Rift Valley, which meets it here. So this is the Afar triple junction, right? So this is called the Afar triple junction, right? And this one, as I said, is called the Indian Ocean triple junction. So these are just names we have for different kinds of triple junctions that are of importance to us here. So you have another one here in the Atlantic. This is a major one called the Azores triple junction, right? And the South Atlantic, right, you have this triple junction here, which is called the Bouvet triple junction. So these are not the only triple junctions. These are ones, the sum of many. Now, I'd call particular attention to a few of the ones that we'll be discussing, right, today. One of the important ones that we'll be discussing is this one here, right? And we'll also be talking about these two towards the end of the class. Now, this triple junction here, right, this is called the Galapagos triple junction. It's famous because this is the location, close to the location of the Galapagos Islands, which were so well documented by Charles Darwin when he was on his journey on the Beagle. So this is of particular, importance to science, really, because much of the theory of evolution really is related intrinsically to the location of the Galapagos Islands here. On the other hand, these two other triple junctions are along the western coast of North America. This is called the Mendocino triple junction, this one here, right? So this one is the Galapagos triple junction. This one is the rough position of something called the Rivera triple junction, J, and this one is called the Mendocino triple junction. Now, as I told you, most of these are the triple junctions that are closely associated with the mid-oceanic ridge system, and that's why these are particularly marked. But we are also going to be talking about some triple junctions which are roughly around here. So this is actually just a defect in my drawing. So this is Japan, and the northern part of Japan itself, there is also a triple junction called the Japan triple junction, which we will be talking about. There are many other triple junctions. We're just talking about a few, just to give you an idea of how the geometry of the plates actually changes on the surface of the earth as you look through it. So now let's look at the Eastern Pacific. So the Eastern Pacific, once again, just to make you recall, so the eastern part of the Pacific Ocean is this one, and we are going to actually be talking about this particular triple junction here. So this triple junction is the one that I talked about here, called the Galapagos triple junction, and I'm going to be talking specifically about the Galapagos triple junction here. So the Galapagos triple junction, it separates the Pacific plate. The Cocos Pacific plate is to the west, the Cocos plate to the north, and the Nazca plate to the south. Okay. Now, the boundary between the Pacific plate and the Nazca plate is a famous one. It's called the East Pacific Rise. It's famous because it's the fastest, it's believed to be overall the fastest spreading divergent boundary on Earth. This is very fast, and this spreading rate is supposed to be 135 millimeters per year. That's approximately 14 centimeters per year. It's the fastest one that we know of now, uniformly throughout its length. On the other hand, the Galapagos Ridge it's actually trending east-west, and this separates the small Cocos plate in the north, from the Nazca plate to its south. Now this one is a slow spreading ridge, and this gives you an idea of the types of the variations in spreading rates that we see on Earth. This is only spreading at a rate of about 40 millimeters per year or so. So essentially, this particular triple junction, it's between three ridges. Therefore, it can be classified or can be considered as a ridge triple junction. Now, let's just look a little closely. So it's just just an extract from a little map to show you exactly what it is supposed to show you. So this is the location of the Galapagos triple junction. So as you can notice, now if I draw this specifically, so you've got one ridge coming in like this, right? This is the ridge between the Pacific plate on this side, right, and the Cocos plate here, right? And then you have the east-west trending ridge between the Cocos and the Nazca plate, and then you have with a small layer, right? This is the boundary. This is the boundary between the Pacific plate and the Nazca plate. So you've got three different boundaries. So this is the one that is called the East Pacific rise, right? So this is the fastest spreading rate called the Nazca plate. The East Pacific rise, as you will see later, its topography itself are different from those of other ridges. It's spreading so fast that the East Pacific rise has a smooth topography. You don't actually have these rift system visible on the surface here, unlike what you see in the Galapagos rift. So this is the Galapagos rift. So you have different segments of ridges, and this is actually joining. This is my Galapagos triple junction, and it's actually proceeding from in a series of segmented boundaries, right, from another triple junction, which is my Rivera triple junction, which we'll talk about a little while later. Now, there is the Galapagos Islands themselves, which Darwin discovered, are here. And so the triple junction we are talking about is actually pretty close to the Galapagos Islands. Okay, so this is the triple junction that we are concerned about. This is the one that we'll be discussing now. It's a ridge triple junction. And because it's a ridge triple junction, if we assume orthogonal spreading on each of these, right, as I told you before, no matter what the geometry, whatever the manner in which I draw the relative velocity triangle, which depicts the relative velocities between these three plates, the perpendicular bisectors of each side of the relative velocity triangle, right, that would be actually, and that would also inevitably they will actually meet at a point. The intersection between the perpendicular bisectors would be at a point which would be the circumcenter of the relative velocity triangle. So this is a ridge boundary, right, in which the orientations would be roughly like, I think they would be this way and this way. Very roughly it would be, well, it's a little bit this way. So you'd probably have one boundary this way, one boundary like that, and another boundary this way, right? So the boundary between the Pacific plate and the Nazca plate, let's say the Nazca would be moving this way, Pacific would be right about here. Obviously this has to be the Cocos plate here. So these boundaries, I may have drawn them very approximately, right? So you get a rough idea of what the part is. So this angle is considerably more than the part here, but just assume that they are more or less parallel. So this is the sort of situation you have. So if you draw perpendicular bisectors, now let's use a different color, right, on this to show you the perpendicular bisectors. So if you have a perpendicular bisector of this line, then the perpendicular bisector of this one here, perpendicular bisector of this one here. So obviously the one here is not correct. So let me just correct that. So if I draw it correctly, the perpendicular bisectors, so they would all tend to meet at this particular point. So this point would be the circumcenter. Now the circumcenter, it means of course that if you can actually draw a circle right around all three. Now what is important here, it means that the distance of the triple junction from each of the three plates is equidistant. That means then that with respect to the magnitude of the relative velocity, the triple junction will actually be moving with the same magnitude, right, of of velocity with respect to each of the three plates. However, it will also be moving in different directions. So this triple junction, if it's located say here, it would be moving southwestwards with respect to Cocos, it would be moving east-northeast with respect to the Pacific plate, and it will be moving west-northwest with respect to Nazca. So although the magnitudes of the relative velocities would be the same, right, nevertheless the actual directions in which the triple junction is moving with respect to the different plates would be different. But the most important thing is it would always be a stable triple junction, because it's a ridge triple junction. So we can actually see one in nature in which we have an actual triple junction which is stable. It's a ridge triple junction. So the famous Galapagos triple junction is one of the ones that we can use to understand this. Now, how about the western? Let's take a look now at the western part of the Pacific Ocean. And there we have a triple junction called the Japan triple junction. Again, let's switch back to red for variety. So the Japan triple junction here. Now, the Japan triple junction, it's at the junction between the Japan Trench, the Izu-Bonin Trench, and the Philippine Trench, right? So there are three trenches which are actually meeting at one point. So this is a T triple junction. So it separates the Pacific plate, the North American plate, and the Philippine plate. And it's a TTT triple junction, as I told you. So all three of these plates, we are now looking at an actual example on Earth, right, of the types of geometries that we discussed in the last class. So let's now just go into looking at the plates once again. So we are now talking about the Japan triple junction. Now, this is the western, this part, if you can see. So just concentrate your attention here. This is the western part of the Pacific Ocean. So all this part is the Pacific plate, right? This is the Pacific plate. This is the Philippine plate here. This is the Philippine plate here. Now, to its north, you can see this is the Aleutian arc, the Kurile arc. This is the Aleutian arc. This is the Kuriles, right? And then you have an arc which is actually becoming the Japan Trench. So you have the Japan Trench here. So you have the Japan Trench coming out from here, right? And it's meeting round about this point, in which you have three trenches actually meeting at one particular point. So this is the Japan triple junction. Now the northern part, now it's a question of whether we think it's the Eurasian plate, this part, right? Whether this part itself here, this region here, whether it's a part of the Eurasian plate or the North American plate. Now there's some dispute about this, and that's what makes it interesting. People are still discussing bits about this. Some people think it's a part of, it used to be at least a part of the Eurasian plate, but now apparently it's actually amalgamated into the North American plate. So the North American plate continues from here. So if you look at the western part of this plate, it continues from here, continues through here, and then continues up to about here. So that's the idea. So you've got the North American plate, the Pacific plate, and the Philippine plate meeting at that particular point. So this is what was indicated when I say that it's the junction between the Pacific, the northeastern Japan, that is the North American plate. I put a question mark because of the uncertainty with, which plate it actually is, and the Philippine plate to the south again. So let's just now try to see whether this particular junction is stable. Now, this is again an extract of the gross geography around this junction. So this is the junction we're talking about. Sometimes the Japan triple junction is referred to specifically as the Boso triple junction. And the reason people refer to it as that is that just west of this, there is another triple junction which people have recently identified, and they think that it is also a junction between the two. So in any case here, let's just see the junctions here. So this is the Japan Trench, right, which is separating, right, the Pacific plate, which is this part. This is the Pacific plate, and it's subducting below the plate here, which is a part of the North American plate. So along this segment of the Japan Trench, the Pacific plate is subducting below the North American plate. That is, the North American plate is the overriding plate. Now, this plate here is the Philippine plate, this one here. So this one here is the Philippine plate. The Philippine plate, again, is actually subducting below the North American plate. So it's actually subducting below the North American plate here, and then it is also subducting, subducting below the North American plate here. Here the Philippine plate is actually overriding the Pacific plate. Okay, so the Pacific plate is subducting also. So the Pacific plate is subducting both along the Japan Trench as well as along the Izu-Bonin Trench. So this is the Izu-Bonin Trench. So this is the source of one of the spectacular igneous rock types called Boninite. There are a group of islands called the Bonin Islands here, right, after which that particular rock is named. And then you have this trench, which we'll call the Philippine Trench here. So you've got three trenches meeting at this particular point now. So you have three trenches. So are these stable? Now, as you can see, the relative velocity arrows are marked here, right? So these are the gross orientations of the relative velocity directions. Now, if you plot them along a trench triple junction, now, so you can actually have an arrow like this, two arrows which are close to each other, right? These are almost close to each other, and this one here, which is approximately this way, right? So you've got arrows like this. So overall, this particular geometry that we see here, because the orientations of the boundaries, now these are, you notice that the Izu-Bonin Trench and the Japan Trench are not collinear. They're not along the same line. And if you remember our discussion from the last, when we discussed the TTT triple junction and a hypothetical case in the previous classes, there I showed you that, I mean, there are situations under which a TTT triple junction can be stable, but there are many more situations where they could be unstable. And so what would happen is that they would actually tend to become an unstable triple junction would tend to evolve into a stable triple junction with time. Now, if this was part of one single continuous collinear line with respect to the velocities here, then we could have considered, right, this particular boundary could have been stable, and that is what it was considered to be for some time. However, now, once it was discovered more precisely that the Japan Trench and the Izu-Bonin Trench are not exactly collinear, it's now considered that this particular junction, the Japan triple junction, right, Japan TJ, or the Boso triple junction, this is most likely unstable, and it is desperately trying to evolve into a more stable geometry with time. So all these triple junctions with time, they will evolve into geometries which are a little more stable. So I've shown you a TTT triple junction, right, on Earth, which is also now, which is unstable, but it's trying to evolve into a stable geometry, because there are some TTT configurations which are stable. So once it is unstable, that means that there would be some change in the geometry. So we are looking at it at an instant in time. It is unstable at this instant. But what it will try to do in the next geological instant, which could be thousands, maybe a million years, right, that sort of scale, it will try to evolve into a geometry which is much more stable, because this geometry, the present geometry, is inconsistent with stability. So let's now go back once again to looking at these plates on Earth. And what we'll do now is to look at the northeastern part of the Pacific Ocean, the part that's here. Now, the northeastern part of the Pacific Ocean is actually very important with respect to the evolution of the whole theory of plate tectonics, because it was one of the ones which was used by Dan Mackenzie, right, together with Bob Parker and later on with Jason Morgan. With Bob Parker, he worked out, right, the rigidity based on the spherical Earth he tried to use, and he demonstrated that these were all, uniform rigid bodies on the surface of the Earth. And then with Jason Morgan, he talked about the evolution of the triple junctions, and that is what he actually tried to show had happened along the western part of the Pacific Ocean. Now, with the Pacific Ocean, there's something that is very interesting. Now, just note this shape of the plate. Now, this is broadly the eastern part of the Pacific. This is the western part of the Pacific. So the Pacific plate is an enormous plate, right? It's huge. And this plate itself, right, much of this plate has subduction zones. There are a few ridges along some of these margins, right? So you've got the East Pacific rise here. You've got the Pacific Antarctic ridge on this part here. But much of this part is subduction zone. Much of this part is subduction zone. In fact, much of the western part of the Pacific is actually bordered with subduction zones. So the net result is that the Pacific plate, even though it's such a large plate, it's actually being consumed with time. But there's one other very interesting feature. If you look at the entire part of the Pacific Ocean here, and you look at the magnetic anomaly patterns, you see that the magnetic anomaly patterns here are actually unpaired. That is, you do not see a reflected symmetry across a ridge here because there are hardly any ridges. The only symmetry that you see would be in small places around the Cocos Plate, the Nazca Plate, a few here, and very few in these regions. There are small, tiny little plates there where you can actually see, but otherwise, most of the anomalies that are there in the Pacific Ocean, in the Pacific Plate, are unpaired magnetic anomalies. So this is a very interesting and important observation, because what does it actually mean? It means it has something to do very much so with the evolution of the Pacific Ocean. As you can see, this is very large, and these are the two triple junctions which I talked about before. This is the Mendocino triple junction, this is the Rivera triple junction, and we'll now talk about the importance that these two triple junctions have with respect to the evolution of the Pacific Ocean itself. Now, the northeastern Pacific, right, in general, it has the Pacific Plate juxtaposed against the North American Plate. So this is the Pacific Plate and this is the North American Plate. So if you talk about the North American, Northern Pacific, Northeastern Pacific, it's essentially the Pacific Ocean against the North American Plate, right? That is what we see. However, there are a number of smaller plates just along the western margin of the continent of North America. Now, importantly, much of the Pacific Ocean or so, only one half of a magnetic anomaly pattern remains. And that is important because it suggests that there must have been a trench that consumed the other half. So you can't have, we know that magnetic anomalies are produced at mid-oceanic ridges. So if you have an unpaired magnetic anomaly, if you have only half of a magnetic anomaly pattern, it means that the other half must have been consumed. So what this indicates is that much of the Pacific Plate must actually have been consumed. The other half must have been consumed somewhere. And it is thought that there must have been another plate which has been called the Farallon Plate, which actually preserved the other half of that particular pattern. And this plate has now been almost completely consumed. So what has been the geological consequence, right, of the consumption of this Farallon Plate? Let's have a look at this. What does this actually mean? Now, let's think of this particular type of geometry. This is, let's say, a part where you had the Pacific Plate here. So this is the Pacific Plate. This would be the Farallon Plate, right? And this is my North American Plate. I would put it as the North American Plate, as it's called now. Now, the Farallon Plate was subducting below the North American Plate, right? It was orthogonal subduction, so the convergence was orthogonal. On the other hand, the boundary between the Pacific Plate and the Farallon Plate, right, was separated by ridges and transforms. Now, we are going to now look at one particular part of this transform. So we're looking at one particular part of the plate here. So we have the Farallon Plate. This part here is displaced across a dextral transform called the Mendocino transform, right here. And there is another transform which is a sinistral transform called the Murray transform at this part here. But we'll now talk much more, right, about this particular transform and how it evolves with time, right? What would actually happen to this particular part? Now, essentially, because of the velocities that are involved, right, this is being consumed, this is being produced here, but the rate at which this is being produced, the rate at which the Farallon Plate was being produced was smaller. The spreading rate, that is the half spreading rate, was smaller than the rate of subduction of the Farallon Plate below the North American Plate. As a consequence, what would happen is that this entire system comprising the ridge as well as the transforms, this would actually move eastwards with time. So this whole system, the whole system would tend to move eastwards towards the boundary of the North American Plate. For the time being, let's consider that the North American Plate is fixed. Now, obviously, as this part moves eastwards, at some stage, the boundary, initially notice that the Pacific Plate has no boundary with the North American Plate along this segment. So there is no boundary between the Pacific Plate and the North American Plate here. However, when this segment of the boundary reaches now, so this point here would be the first part to actually touch the subduction zone. So it means that as this is being consumed, right, this boundary between the Mendocino transform and this segment of the ridge would actually be the first to strike it here. So you would actually develop a geometry along which a dextral transform, a dextral transform like this, right, would be intersecting a subduction zone here, right? So this plate is what is left of my Farallon plate, and this is my North American plate, right? And this now is the Pacific plate, right? So the Pacific plate, there's still a ridge here, right? But the Pacific plate, this is the first point along which the Pacific plate comes into contact with the North American plate, and a triple junction is formed. Now this triple junction, as you can see, is the boundary between a transform fault, a trench, right, and another type that we don't know, right? We don't know what the nature of the boundary would be between the Pacific plate and the North American plate as this system evolves further. So now, as it moves further, this particular ridge would tend to be consumed. So in fact, if I go down, right, this is the sort of geometry which would evolve here. Now, what would happen along here? Let's just think of, let's call this is the what is left of the Farallon plate. This is Pacific, and this is North America, right? Now, we've marked them in terms of A, D, and C. So what would be the nature of the boundary between C and A? This is what is of importance to me, because this is what I do not know, right? So we can actually express in my typical form. Here we'll just use the terminology or the plate vectors as they are used here. So let's say the relative velocity of plate A, right? This is the North American plate. The relative velocity of plate A with d of plate D with respect to plate A, right? We can represent it in this form, plus the relative velocity of plate C, right, with respect to plate D here. Now D here represents the Farallon plate, right? And A here represents the North American plate, C represents the Pacific plate. Now let's take this, the relative velocity between the Farallon plate D, right? The Farallon plate D with respect to plate A. So this is the relative velocity, so we can actually mark it out here. So this would be the relative velocity. We can think of this being the Farallon plate D. This is the plate, this is D here, and this is A here, right? Now, this is, now we've got the relative velocity of C with respect to D. Now, how does C move with respect to D? Now, the relative velocity of C with respect to D, now C is moving this way with respect to D. So, the relative velocity of C with respect to D, C would be at this point because it is moving with respect to an observer on C. C is, this is actually a dextral transform fault. So C would appear to be moving to the west to an observer on D, right? So this would be relative velocity here, which means now the relative velocity of C with respect to A, the relative velocity of C with respect to A would actually have to be in this orientation. Notice that this orientation, now if I take this vector and put it onto this plate here, right? So this would be, this vector would be on this magnitude, right? Obviously the opposing part would be here because this vector turns out to be parallel to the orientation of the North American coastline. In other words then, automatically the boundary, the third boundary that has evolved, the new boundary that has been formed between the Pacific plate, which is plate C, and the North American plate, which is plate A, would turn out to be a transform fault. So this boundary now would be a transform fault. It would be a dextral transform fault. Now today we have a name for this dextral transform fault. We call it the San Andreas fault. So this really is a spectacular example of how the San Andreas fault, which is the celebrated fault passing through the major cities of San Francisco and Los Angeles, right, and along the western part of North America, how this has evolved. Now, what it has also resulted in is the formation of two different triple junctions. So this triple junction here, right, this is called the Mendocino triple junction, right, the one that I showed you earlier. This one, the southern end, is called the Rivera triple junction. So we should look at them separately, but just as an example, I'm just telling you how to actually be able to reconstruct this. So this would actually turn out to be an FFT triple junction, right? So an FFT triple junction, two faults and a trench, right? That is what the present day Mendocino fault is, and that is what the San Andreas fault has become. Now, if I now try to draw in the position of the triple junction here, we know that the with respect to the plates A and D, right? So A is the overriding plate, right? A is the overriding plate, D is the subducting plate. So if A is the overriding plate, that means the trench is attached to plate A, right? And so the velocity that I'm dealing with would actually be passing through here. So the boundary, the relative velocity of the boundary between A, the relative velocity of the trench would be attached to plate A. It would be here. So the boundary itself between plates A and D would be actually parallel to this boundary. This is also parallel to the AC boundary, which is also here, right? And the third boundary, which is the boundary between C and D, is also here. So the position of the triple junction would actually be out here. So to an observer on plate C, the triple junction will not appear to move with time, because essentially it has the same velocity with respect to this. But then to an observer on plate D and an observer on plate A, it would appear that the triple junction is moving with plate C. So to an observer on the North American plate, the Mendocino triple junction would be appearing to move northwards along the coastline, right? To an observer on this part of the Farallon plate, right? The Farallon plate, that particular triple junction would simply appear to be moving westwards. What is important here is now this plate, this and this were previously part of the same plate, if you remember. So this was previously part of the same plate, but now this segment and this segment are distended. So as it's distended, now these are two separate plates. This is now called the U1, the Fuca plate. So it's actually regarded as a small segment. It's now regarded as a small segment, right, of the Farallon plate. So it's just a small segment of the Farallon plate that is still preserved, right? And this is a small segment of, you can call it the Rivera plate, right, which actually passes into the Cocos plate further south. Okay, so this actually is a very interesting example which actually shows you how plate boundaries move with time. Similarly, actually, the Rivera triple junction, if you do the velocity, draw the relative velocity triangles around here, this appears to be moving southwards, which means that the San Andreas fault is actually lengthening with time. So the boundary, what used to be a convergent boundary between the Farallon plate and the North American plate, is now slowly being converted into a transform boundary, which is today represented by the San Andreas fault system, the strike-slip transform fault. So we now have a perfect example of how the San Andreas fault was formed between the Mendocino triple junction and the Rivera triple junction. However, there is some uncertainty as to whether the Mendocino triple junction is stable. Now you might wonder why that is. And that is primarily because although the broad overall coastline, I've drawn it as if it's in the northwest southeast direction, there are segments of the boundary, particularly here, which actually have a configuration which is a little like this. So it's a little north-south. So when it becomes a little north-south here, then the exact trend of the boundary when you mark it through doesn't exactly pass through where you'd feel. So the geometry would evolve. And that is where certain things, very interesting things, begin to take place in the western part of continental North America, just east of the San Andreas fault system. So it's actually thought that maybe the Mendocino triple junction is actually not stable. It's evolving into a stable configuration, but right now it's probably unstable, primarily because the position of the North American coastline, right, the trench which define the North American coastline, is not exactly parallel to the velocity vector, that is their velocity vector represented by the San Andreas fault system. So to conclude then, in today's class, you saw three examples. One is the Galapagos triple junction, which is a ridge triple junction, which is stable. I showed you a Japan triple junction, which is a TTT triple junction. Could have been stable, but in its present configuration, it's just moved out of stability simply because the Isobunin trench and the Japan trench are not collinear. The Mendocino triple junction and the Rivera triple junction, these formed as a consequence of the subduction of the Farallon plate below the North American plate. And then what the final message of the beautiful, it's a beautiful example of how we created one of the most spectacular features known on Earth, the San Andreas Fault. But it was created because of the subduction of a plate that existed previously, the Farallon plate, the counterpart of the Pacific plate, which we can no longer see. So this gives you an idea today of how movement of triple junctions on the surface of the Earth actually results in very interesting changes taking place on the surface itself. Things change on the surface of the Earth simply as a consequence of plate motion, and the geometry of plate movements actually dictates this. However, all of what we've discussed so far has been talking about the Earth as if it's a flat Earth. Unfortunately, or fortunately, I would say, the Earth is not flat, it's a sphere. So what we need to discuss in the next class is what would happen, right, if the Earth is spherical. How would we modify this theory to fit into what we see on the spherical Earth? So follow the same examples, the same references that I actually talked about. So the book of Fowler, the paper of Mackenzie and Morgan, and the Moores and Twiss book, right, on tectonics. These are the main books that you can use following this. Thank you very much.